Hello all. So this is the 14th lecture for our smart sensing course, and we are going to continue on the frequency domain today as we have started on the last day, right? So as a simple recap of whatever happened in the last class was we started formalizing our coiling machine, and we introduced the notion of the weight that we wanted to assign to each one of the frequency components that we were computing. And there is a slight change in notation that I have done here. So earlier we were using n from 1 to small n, from 1 to capital N, whereas I have updated the notation slightly. This is basically 0 to n minus 1. So we have the first frequency component starts with a 0 offset, right? Whereas on the bottom side, I show the n time domain samples starting from x0 to xn minus 1, and the weights that we compute for the n frequency components are w0, w1 through wn minus 1. So one thing that you should note is all these weights are still complex values, right? Because when we were talking about this analog of the center of mass thing, right, that we were trying to compute for all the samples, that was distinctly computing on x component and an y component, which we sort of coalesced in form of a complex number represented by this Eulerian notation here, right? E to the power j phi n or e to the power j 2 pi k by n into small n, right? Where n is the nth sample. Okay, so you have to see that once you compute this particular expression, right, this entire expression, it still will have two components, right? There is a real part and there is an imaginary part, and we can always take the ratio of them to find out the slope of that particular sample in the complex plane, and from there we can also like calculate this phase of it or the angle, right, which is basically tan inverse of that particular slope. Okay, so either we can look at the absolute value of these numbers, right, where we can compute the absolute value or the magnitude or the weight as w k is equal to it is the real part of the wk, right, which is the real part of the wk plus, so this is squared, and then we have the imaginary part of wk, which is also squared, right, and then we take the square root of this, right, which is basically giving us the magnitude. Okay, or we can also just stick to the real component and just throw out the imaginary component completely, right? So there are like different ways we can find out the weight. So so this is just a simple note about this frequency components, which are again complex numbers. And also please note that this the phase part, right, where you have the imaginary component and the real component. If you take the ratio, then we can find out the slope, right, and getting a tan inverse of this particular quantity is going to give you the value of phase. Okay, so for every component basically, then we can get a magnitude as well as a phase, or you can call it an amplitude as well as a phase. Okay, so as we also mentioned in the last class, the kth frequency component doesn't necessarily mean it's k hertz, but there has to be a mapping that has to be done from all the frequency components to the range of frequencies that could be potentially mapped by this frequency extractor device, right? It could be 0 to 100 hertz, or it could be 0 to 50 hertz, and so on, and based on that every frequency value will be mapped to a certain frequency component. Okay, and then we started looking into real signals where we were using the step counter data or the heart rate data coming from the IR sensor or the photodiode, and we were collecting the intensity values to compute certain events, right? In this case, where we were looking at the heart rate, we were using the pulse oximeter device and looking at this periodic data that was coming out from the red LED or the IR LED. And in case of the step counter, because of the movement of our legs and hands, we were getting a periodic function or like a periodic data. And this could all be input to the frequency extractor device or the coiling machine, and is going to churn out the frequency components that are potentially present in the particular data set. Right? So if we have n samples, we basically can compute n components. Okay, and then the other thing that we are going to look at is the running an actual frequency extraction of the data that we already have. So we happen to have this 32 seconds worth of data, which is basically the IR intensities coming out from the pulse oximeter because of placing our hand in between the IR LED and the photodiode. And the data that was being collected was at a rate of 16 samples per second, which comes to about 512 samples, right? So in this entire stretch of 32 seconds, we had 512 samples, which was sort of uniformly spaced, right? If it is not even exactly uniform, but it's somewhat uniform to some kind of tolerable margin, right? This is important, right? We cannot have some second where we have 50 samples, and we cannot have another second where we just happen to have like 3 samples or 5 samples, right? So there has to be some uniformity in the sampling that has to be maintained. Otherwise, all the mappings to the frequencies is going to change, right? So we are going to look at why and so on. So this is something that we have already looked at in the last class, where we were specifically looking at n/2 frequency components, and we are soon going to see why and what happens to the other n/2 components and so on. So first, let's quickly check on the coiling machine, where we feed this 32 seconds worth of data, and on the right hand side we keep on plotting the average weight, right? So this is basically 1 by n sum of an e to the power j into phi n, right? And we do it for n/2, which is 512 divided by 2, that is basically 256 frequency components. Okay, and there we can always keep track of the dominant peaks, right? We could very easily find out 2 peaks. One is located here at an offset of about, let's say, maybe 40 or 40 or maybe around 50, and there is something here, right, which is approximately around 100, right, and so on. There are some of these things that are sort of repeated, right? And as I told you, we can ignore some of the components that are coming towards the very beginning, right, which is basically, for example, the frequency component coming at like the weight being computed at frequency component 0 means that there had been no rotation of the entire signal, right, which means that all the signal or the sample components were just parked at 0 degree, right, or 0 radians, which means we'll have all the samples stacked up here, which is going to produce a very high value of the center of mass that we were talking about, right, which is going to give you an very abnormally high component amplitude, which is going to be very high compared to the rest of the components, right? And that's why I have kind of deliberately stripped off some of the initial values, right? The initial values of the frequency components, 1 or 2 of them, and which is basically making sure that the rest of the components that we are interested in are sort of visible, right? This is something that we are interested in, right? We want to know the variations here. So these are the dominant frequency peaks, and we have to figure out though that what does this particular component mean, right, in terms of physical cycles per second or hertz, right? These are just frequency components, or whatever we call as like W of WK, right? It's the kth weight that is assigned to the kth frequency component, and we still don't know what that frequency component corresponds to in terms of actual frequencies, right? So what we have seen till now is the first n by 2 frequency components, and we have a pretty good idea about uh, what it means, right? And the other thing that we wanted to also look at, just for completeness, is why do we suddenly look at the first n by 2 components? What happens to the rest, right? What happens to the n by 2 at n by 2 plus 1 till n, right? Because we were supplying n time domain data samples, and we are expecting to have n components, right? Why do you suddenly look at n by 2 of them? So instead of giving you an explanation, first let's start with actually looking at running the coiling machine further, right? So after crossing the 256 mark, what happens? So we'll very quickly plot the components from 0 to 256 and then see what happens after that, right? So the frequency component that I'm plotting here could be slightly off, right, because of the stripping of some of them. And now see, I have reached n by 2 and then increasing the value of n further, right? From n by 2 onwards, it goes all the way to n. So it will go till 512, and I have stripped off some values from the beginning and the end. So you will see the effective number of components that I'm showing here. It's a little bit reduced, but this is just because of the code that I have written, right? I can always map it to show the actual component that has been computed, right? So I'm actually stripping out some of the data points from here and some of the data points from the beginning, right? That's why you see a slight variation. Okay. So if you see what is interesting here, anybody could understand very quickly, is what we see is some sort of a reflection, right, across the line that has been drawn through the n by 2th component. Right? If you see the dominant peak, which was happening somewhere around 50, right? This offset, right? If we call this offset as delta, right, we see a very similar offset delta here, right? Same for the other ones, right? So if we see, call this one as let's say lambda, we can see a very similar offset from the other hand side, which is again lambda, right? So what is the cause of all these things, right? And you can also appreciate, right, there is a definite redundancy if we look at the other side of n by 2. So what we were doing in the very beginning was we were trying to look at the 0th component through the n by 2th component, and when we do look at the components which are beyond n by 2, apart from the reflection, at least you can understand that there is a definite source of redundancy in the data. Okay. So what exactly causes this, right? We are sure that there is something that is going on in the winding machine that is creating such a reflection, right? So can we explain what is going on, right? So let's try to analyze that. So first I'll give you some examples, the offset example that I have given you. So on the top, I am showing you the component ID or the component number, right, which is 3, right? Or 3 is basically the offset or the delta or the lambda that I was referring to in the last slide. And this maps very clearly to some other component on the other side of n by 2, right? So if you see, the patterns are exactly similar, just that the pattern has a reflection, right? So the coiling machine's output, right, the way we were turning the signal across our imaginary circle at a certain rate, that exactly reverses, right? Whereas we start from this side and go this side and so on, and this side and so on. So while we do the same operation, here we end up in a pattern which is the exact reflection uh, of the top figure, right, or the top pattern across the line 0 across x-axis basically. So this is the, in the polar coordinate, it is the 0th degree, right? So if you see, so this part gets mapped here, right, whereas the other part, mark it in green, gets mapped on the other side, right, which is very similar the for the other case, right, where we have this 128th component which is being computed, and there exists another component like 384th one, which is a reflection of the pattern that we received at 128th component, right? And what we were measuring is the weight, right? What we were looking at was not this individual data points, but the sum of all the data points and then averaged it out, right? So what we were looking at was not just these individual pieces, right? What we were looking at was the W of 128 or W of 3, right? Or W of 509, or here W of 384, right? So we were actually looking at the magnitude of the center of mass, right, which gave us exactly equal values, right? But what you will at least appreciate from here is there is a definite difference in phase, right? Although the magnitude is the same, but there is a rotational deviation from the top to the bottom one, right? So they are not exactly aligned with respect to the rotational axis. Okay, so you can very easily understand this, right? Whatever is here in this figure goes to somewhere else, right? It actually goes to the right hand side, right? Everything on the left hand side gets reflected, so it basically goes to here. Okay, so if we look at all the n data points starting from the 0 to, if we go to n, and we look at the, if we look at the samples number as an intersample angular spacing. So what happens is, if you uh, make the coiling machine turn at a rate of 0 hertz, which actually means that the intersample spacing is 0 degrees, right? So there is only at 0 degree all the sample gets stacked up, which is very same for the 2 pi case. So the 2 pi thing is again getting overlapped with 0. So if you, even if it is 2 pi, the same phenomenon happens, right? All the samples are actually stacked up, right, at again 0 or 2 pi. It's the same thing, which basically gives you an indication that the large value that was supposed to happen at 0 also should happen at 2 pi, right? There is exactly a 2 pi radian rotation. Okay, and then very similarly you can argue that we can look at these two components, which is k and n minus k, and because this k is sort of an offset that we can assign here, and this is similar offset that we can assign from the other hand side, and we can actually look at the value of phi, right? What is the value of phi for all these samples? So if you look at the first one, which is k, this is 2 pi k divided by n, right? This 2 pi k divided by n multiplied by, for a given sample, it will be multiplied by small n, right? And then we are summing it over. But this is the this is the angle which is formed by two successive data points, right? Two successive samples in the signal. So I call it the intersample angular spacing. So if you remember, we started from 0, the next one would be 0 plus 2 pi k by n, right? And the next one would be 2 pi k by n into 2, the next one would be 2 pi k by n into 3, and so on. And what we were doing, we were trying to find out the average of that. Okay, if you look at the other side, where we were trying to analyze the n minus kth frequency component, in that case, instead of 2 pi k by n, what we'll have is k will be replaced by n minus k, which is same as 2 pi minus 2 pi k by n, right? So this basically becomes your inter sample angular spacing, right? And then you multiply this by 1, 2, 3, and so on. That will be basically give you the phase offset or the angular offset. Okay, hope this is clear. Now, this directly is computing the magnitude of the weight, which is Wk, and the other one is computing the magnitude of W of n minus k. Okay. Now you can very easily appreciate the fact, right? You just need a little bit of knowledge in trigonometry, which is very high school level knowledge, is that what I am basically doing is subtracting theta from 2 pi. So that's all the difference that we have. So there is no difference in magnitude or the amplitude in these two cases for k and n minus k. But basically, if you take the magnitude of it, but if you try to look at the phase that I was mentioning earlier, right? If you look at the ratio of the imaginary to the real, and then considering their sign also, and then take a tan inverse of this particular quantity, there will be some difference, right? And that is what we are trying to explore here, right? So if you actually expand it, and I would ask all the students here to expand this quantity, right? This is just a compressed notation in the Eulerian form. I would ask you to represent it in terms of sine theta plus j into cos theta, or like cos theta plus j into sine theta, right? And then try to see how it expands. Okay. So I'll do some of the work for you. On the left hand side, if you see, if we concentrate on this phi of n, we can see it can be expressed as amplitude n for a particular sample multiplied by cosine of phi n plus j into, this is just to denote the complex angle, into sine of phi n, right? And whereas for the other case where we were trying to look at the n minus kth component, so this is basically for the kth component and the nth sample, right? The nth sample while calculating the kth component. And here we are basically trying to look at again the nth sample, but in the n minus kth component, right? We are trying to look at the n minus kth component and still the nth sample. Okay, so what happens is phi of n is exactly going to be 2 pi minus phi of n, right? That we have already seen, which basically becomes the cosine doesn't change the sign of it, so it's basically cos of phi n again, whereas sine of 2 pi minus phi n will become minus of sine phi n, right? So the thing that I've highlighted here is the magnitude still remains the same, but there is an exact change in the very specific change in direction, right? There is a specific change in angle of the particular vector, right? So in the complex notation, the direction that the kth component is going to point to will have a very predictable like orthogonal kind of relation with the direction that n minus kth component is going to point to, right? Hope this is clear. Okay. So I'll explain a little bit more, and then this kind of things is something best appreciated if you sit down, write it up, and then, or even try to simulate it, right? The way I asked you to simulate the coiling machine yourself, because that will give you much more clarity into what is going on, right? You can very easily track when the how the sign flips and so on. Okay? So a little bit more details from the coiling machine, right? So we don't have any problem with 0 and n. We have understood that it exactly gets stacked up at both at 0 as well as n, which is again a rotation of 2 pi. Also, we can say this is like one sample per rotation. So you are trying to calculate n frequency components with n samples. Okay, so we have n frequency components that we want to compute, and the input to the coiling machine is n samples. Okay, so This basically means there is only one rotation uh, or one sample is present per rotation. So this should be understandable, right? You would understand. The same happens for 0 also. Okay. So now what we are doing is we have seen that there is a mapping, right? We have some relation in mind that this kth component and n minus kth component, we saw that there is a definite similarity or definite equality, I would say, in terms of magnitude, and in phase they are a little bit off, right? So how to basically place them in our same picture, right? How do you basically look at it when you look at the spectrogram or when you look at the different frequency components, right, from 0 to all the way to n. So now if we just have this another line, right, which again does a mapping for all these n components but a little bit shifted, right? What we do is that we cut off this particular part which goes from n by 2 to n, and then bring it to this part, right? We basically map it to minus n by 2 to 0, right? Why? Because this particular component, which was n minus k, the n minus kth component on the top, gets directly mapped to something called minus k, because we have already seen that this 2 pi minus 2 pi k by n could be mapped to minus of 2 pi k by n. Okay, so this is very easy to represent and uh, kind of formalize, right? So if this one is plus 5, right, if this is like a plus 5, this will very simply be minus 5, right? And we can even call this components. So if it is a plus kth component and this is the minus kth component. Okay, so n by 2, by the way, will have 2 samples per rotation. So what will be the difference in between them? It will be pi, right? Whereas in the other case, if we go down the line in the backward side, it will be minus pi. Okay, it's basically depends on the direction of rotation. Okay, so if we are having a certain convention about what is the positive direction of rotation, if we go to the other direction, pi degrees will basically end up in the minus n by 2th component. Okay, so just with the example that we just now saw, uh, we call this minus n by 2 to 0. We were not using it but per se, but they exist and we call them like negative frequencies. It basically denotes that the direction of rotation has to be reversed, right? If we try to move, if we have the convention of rotation as let's say anti-clockwise for positive frequencies, then we have to use the notation of clockwise for negative frequencies, right? So this is just a convention and we have to follow the same convention, right, to have a formal notation of this particular thing, right, to formalize it mathematically. But as far as our understanding is concerned, you can say that we are dividing this n components into 2 portions. One is what we get beyond n by 2, that is n by 2 to n. This is mapped to a set of negative frequencies, which is denoted by minus n by 2 to 0. So these are the negative frequency components, and we have 0 to n by 2, which are the regular positive frequency components, and what is basically being used for all the practical purposes that we will see, right? So there is no change in the 0 to n by 2 part. So it's often better to look at just the first n by 2 for all practical purposes. And so this one more example just to reinforce the idea in your head. So if we run the coiling machine, the whatever the algorithm that we had, and if we look at the frequency components starting from 0 to n, we will see something like this, right? Where we can see a stark reflection that happens at the component number n by 2. Okay, what the real FFT or the DFT, will come to that notation later, or the real distribution of the weights across the frequency should ideally look like is something like this, right? We are going to take that up and move it to the other part of the frequency axis, right? So that basically maps to minus n by 2 to 0. So hope this is clear. Okay. So now we come to the, now we ideally know how the stitched version looks like from minus n by 2 to n by 2. So earlier we were trying to look at 0 to n. So earlier we were trying to look at 0 to n, right? Now after computing all the weights across the different frequency components, we now look at the stitched version as minus n by 2 to n by 2. So this is the thing that you have to look at. And particularly if we are just interested about the positive frequency components, we are just going to look at 0 to n by 2. Okay. So it's all centered around 0. That's what you need to remember. It's centered. So this is important. It's centered around 0. It is a 0th component or 0 radians, which is basically the inter-sample angular spacing. Okay. So now we can understand how the stitched version of the FFT looks like, right? So now we have to start working on mapping these frequencies. Okay, so I would say mapping the frequency components. So we have this thing from minus n by 2 running all the way to n by 2, and what the Nyquist sampling rate tells us is that, let's say there are n samples that was collected uniformly. So this uniformly is sort of important here in t seconds. So what is the sample rate? The sample rate is n divided by t, which is the number of samples collected per second. Okay. So the what the Nyquist theorem tells us is the maximum trackable frequency using this data set is going to be s divided by 2 hertz. Okay. So if your sample rate is let's say 50 samples per second, we can track up to 25 hertz, right, which is 50 divided by 2. So if you are trying to track higher frequencies that may be again present in the same data, you need to bump up the sampling rate. So if you are so this is kind of important, right? Whatever phenomenon that you are tracking might contain high frequencies, but to track them in the frequency domain, you need to have the appropriate sample rate. So if you already know that your maximum frequency component which could be present inside this data is, let's say 50 hertz, right? So in that case, you need to make sure that you are sampling at least your sample rate is greater than equal to 2 multiplied by 50 hertz, right? So your sampling rate is at least 100 samples per second. Okay, samples per second. This is not hard. This is samples per second. So we are mostly interested in this 0 to n by 2, and for the completeness, we are also looking at the other part, which is the thing that we have just now saw in the last slide. Okay, so and what we are mapping here, the thing that we are mapping is the values of the frequencies. So till now we were talking about the frequency components, and we were talking in terms of frequency components. Now we are dealing with the actual values of the frequencies. So if max is s by 2, right? If s is the sample rate, the maximum trackable frequency is s divided by 2. Okay, and similarly the f mean, the magnitude is still the same. The f mean we can track is minus of s by 2. Okay. And again, for all practical purposes, we are primarily will be restricted to 0 to n by 2 only. Okay. And this is just FYI, is that the 0 hertz amplitude I have not shown because it is going to dwindle down all of the remaining components. Right? It will be so high that in proportion this will be so less that this will this and this and this will all look like the same amplitude, right? So it's always a good practice to look at 0 to n by 2, and then again I would say strip off the first 1 or 2 components just to make sure that you can finally appreciate the values right here, right? Whatever or the kind of the active part, right? Right, where all your I would say useful frequencies are present. Okay, so this part you can always get rid of. Okay, so now we understand that given the sample rate of the data points, we know what is the maximum frequency, right? Or what is the frequency corresponding to the n by 2th frequency component, which is basically sample rate divided by 2 hertz. Okay, so now we will start the exercise of interpreting the different frequency values. Okay, so this is the example from the pulse oximeter data, and we were using different uh, lengths or different segments of the time series data. The first one was n is equal to 160. This is basically a 16 or a 10-second worth of data collected at 16 samples per second. And this is, as we just now saw, is a 32-second worth of data. So all of them will have multiple cycles in it, right? In 10 seconds, you will have many such heartbeats, right? Right? It's not that the periodic thing is completely absent in it. So both of them will have it several number of times, right? But what is interesting here is that when you do the computation of the frequency components, so if this is 160, the extreme value will be 80, right? And if in case of the other one, if it is 512, so the extreme component on the right hand side ideally should be 256. Okay? So what I'm trying to say is that there is no difference, although the numbers are different. In this case, this is 80, and on the other hand, for this case, this is 256. There is actually no difference in terms of how this maps to the maximum frequency that could be tracked. So here 80 refers to 8 hertz, and in this case also 256 refers to 8 hertz. So there is no difference in that. Okay, so this can map to 0 hertz till 8 hertz. And the other thing that is worth noting is what is the resolution that we are getting. Of course, if we are taking more number of samples, we have to get some benefit, right? So one of the benefits that we get is what is the interspacing in terms of frequency in between the two successive frequency components. So if we have the k minus 1th frequency component and the kth component, the resolution that we are getting is s divided by n hertz, right? So very easily you can understand that 0 to n by 2 spawns the frequency range of 0 to plus s by 2, and in terms of samples is 0 to n by 2. So s by 2 divided by n by 2 gives you s by n hertz, right? So if you consider 160 samples that has been spawned from minus 8 to plus 8, and right, because the value contribution on the positive part is just 80 samples or 8 hertz. So 80 divided by 8 divided by 80, or 16 divided by 160, which is basically 0.1 hertz, right? Whereas if you are having higher number of samples, then your resolution improves. So the two frequency components that we can now tell apart is kind of far more granular, right? So if you increase the number of components, your frequency domain components that you are going to tell apart will be kind of more granular, right? But the thing that you have to keep in mind is, doesn't matter what is the length of the time series. It could be 100 samples, as you see here, hundreds of samples, or even it could be thousands of samples, right? Or millions of samples, doesn't matter. What is the maximum trackable frequency? That is a function of the sample rate. Okay, this is extremely important. Okay, so sample rate is what plays a role in the maximum frequency that you can track. Okay, so if you increase the number of samples, here that you are feeding to the coiling machine, here, your resolution might increase, right? That will not increase the frequency. Okay, so you need to understand the difference in between these two particular things. Okay, so if at a certain frequency, right? Let's say this is, k. So this is will be rho into k hertz. As simple as that. Okay, so now you have a way to figure out, if you know a certain component, what is the corresponding frequency value for that component. That much you can understand now. Okay, so we'll go back to the pulse oximeter data and trying to figure out the beats per minute in terms of with using the frequency domain tools, right? You could always do a peak detection, count the number of peaks per unit time, and in that way solve the problem. But you can also do it in using the frequency domain tools, right? So what is the input? The input is, we have 20 seconds worth of data here, and this 20-second worth of data maps to 320 samples. Okay, so 16 samples per second maps to 320 samples. So you all in all you have 320 samples collected at 16 samples per second. Okay, so what is the maximum frequency that can be tracked? It does not depend on 320. It depends on the sample rate of 16. So what we can map is from -8 through 0 through 8, and if we are just interested in the positive part, right? So this is like 0 to 8. The maximum frequency that we can track is 8 hertz. Okay, and what will be the resolution of the frequency components? So this will be 8, and we are spawning here 160 samples. This is n by 2. So 8 divided by 160 gives us 0.05 hertz per component. So that is the inter-component spacing. Okay, so if you have two successive components, the two successive components are spaced apart by 0.05 hertz. Okay, so this gives you a mapping. So if given that what is the component of corresponding to this peak, which is basically the dominant frequency. So this is the dominant frequency. Okay, so we need to know what is the dominant frequency here. So here it is 28. Let's say 28 is the offset of this particular peak, right? So basically we have 28 components or 27 components before this, and we are at the 28th component. So the peak component is 28. So what will be the peak frequency? 28 multiplied by rho, which is 1.5 hertz, right? So for this particular data set, we can figure out that your heartbeat was at the rate of 1.4 multiplied by 60, that is 84 beats per minute. Okay, so this is sort of an average that happens within this 20 seconds duration. Okay, so this could change if you say slightly, if we basically analyze the first 10 seconds worth of data and then analyze the next 10 seconds worth of data and so on, right? But here we can see that for the entire data set of 20 seconds, we can appreciate that the 28th frequency component has peaked, and which corresponds to a value of 84 bits per minute. Okay, so now we have all looked at our version of the coiling machine. Now there has to be a formalization that is followed in standard literature, right? Because we need to standardize this coiling machine in order to have communication between different parties, right? So earlier this was our sort of analog of the frequency component analysis phenomenon. So we had our own kind of notations and so on. So the formal notation was is this on the left hand side, and this entire thing was proposed by Fourier, and what we just saw was basically the discrete Fourier transform, or DFT, right? So why discrete? Because we were looking at discrete frequency components and discrete time domain components, and the only difference that we have with this particular standardized version of the FT is, if we note, that is a negative sign here, which we were not using. So this is again just a convention, which means what is the positive direction of rotation and what is the negative direction of rotation, clockwise or anti-clockwise, right? And the other thing that is missing here is the 1 by n thing, right? We try to kind of average out the weight, right? Once you find the center of mass, we try to find out the average value in the x direction and the average value in the y direction, whereas in the standard version of the Fourier transform, that doesn't exist, right? And this is the expansion, because it was shortened using the Eulerian notation. This is the expansion that you can very easily see. Okay, so this is the, in the standard form, if this is negative, so if we use a minus phi here instead of a plus phi, this sign will change to positive. Okay, so this is the convention that we follow in this particular notation for the discrete Fourier transform. Okay, and I have already asked you guys earlier, right, what is the time complexity. You can very easily appreciate that for calculating n frequency components on a time domain sample of n data points is n multiplied by n. This is n square, right? Because for every pass of the coiling machine is linear, that is order of n, but you are making n passes, right? Because you are trying to find out the frequency component from 0 to n, right? Even if you do it from for 0 to n by 2, that still is n square, right? Order of n square. So there is a definite improvement, which is a version known as the first Fourier transform that was proposed by Cooley and Taki. So that is a very famous algorithm called the FFT algorithm, which reduces the complexity from n square to n multiplied by log n. Right? This is a huge improvement that was achieved, and that's the reason you have FFTs running on all sorts of low-end IoT devices, right? So n square, it would have been ideally if you just have a naive implementation that we did as a part of the class initially to understand the concepts involved. You can look at how the first Fourier transform is implemented. So this is not of much interest for this particular class. If you are more interested on the algorithmic piece about how do you implement a faster version of discrete Fourier transform, you can look it up, right? And in terms of users, right, we can have a lot of implementations of the first Fourier transforms that are available in the NumPy libraries or the SciPy library. SciPy has a more detailed sort of more comprehensive set of functions that are available, right? You can look at the particular web pages and figure that out. And primarily we take two inputs, right? One is the time series vector. So basically these are the time ordered samples, and the other one is the number of frequency components that you wish to compute, right? So this is always not n mapped to n. So this n could be thousands of values, right? It could be having 10,000 values, right? And at time we are, let's say, interested in figuring out only 1024 components, right? So if you give more number of samples, it will sort of average out and the noise gets apart and so on. That we'll very soon see, right? And this is also known as frequency components or frequency bin. Sometimes instead of saying that a particular component maps to a definite frequency, we can also say that this maps from frequency f to frequency f plus rho, where rho is basically the resolution. Okay? So if this is, let's say, 50 hertz, if f is 50 hertz, f plus rho could be like, let's say, 50.05 hertz, right? So this is basically a frequency bin, and we assign a particular weight to this bin, right? Either you can call it a component, you can call it a frequency bin, and so on. Okay, so this is the number of bins or the number of frequency components that we wish to compute. So I would encourage you to use this first Fourier transform. So it's just a function that is going to calculate all the 0 to n components, and you can look at that how this reflection thing happens, and you can always strip out the n by 2 to nth component because we don't need them, and you can just look at the first n by 2 components. So if you ask why choose a larger FFT size, right? You can use, let's say, more number of samples, but within the more number of samples, we can choose a smaller FFT size also, right? We can choose, let's say, 16, right? Versus we can choose something like 1024, right? So what is the reason that we have to choose a larger FFT size, or when it is required, right? So as you see in this particular case, doesn't matter much, right? If we are using less amount of data, or if we are using n, which is basically the number of bins or number of components in the FFT, also of a lesser number. In this case, they are equal. So but we are going to see the rationale behind it. In this case, this sort of doesn't matter. We are able to find out the peak frequency component, the dominating component, and this is going to give us a correct value of the BPM, right? We were, in this example, we are more interested in looking at the value of bits per minute of our heart rate, right? And what happens is real world signals could be noisy, right? And sometimes they are very, very noisy, as we will soon figure out. So higher the number of samples, that could help you in cancelling some of those noise, right? If we increase the number of samples, or if we increase the size of the FFT, which in turn takes more samples, because if you are having an FFT of size 1024, it is of course going to look at 1024 samples, and then it could look at more, right? It is going to average it out. So that is inherently going to consume more samples, which is going to cancel out some of the noise. Okay, so there could be all sorts of random noise that is present in the data. So this could help you reduce some of it, and we can just give you an example to appreciate this particular fact. So this is the natural noise that was present in this IR data. Okay, and right, you can see there is some anomalies. There is a little bit of noise present, and when we do a 64 bin FFT on this real trace, we can very easily figure out the peak component, right? The frequency, the resolution of this could be less, but doesn't matter. At least we can get a very sharp peak, right? This is a sharp peak in the first Fourier transform. Okay. However, let's say if we add some kind of a synthetic noise on top of this, right? I did not have like a particular noisy data to compare with. So what I did was I took this data that already has some natural noise present, and I added a little bit of noise to every sample, and we did it in 3 stages. In the first case, we added some moderate noise. So once we added the moderate noise, we can still find the peak, right? But I would say it is less sharper. So why it is less sharper? Because what makes a peak sharp is basically the neighbors, the neighborhood peaks, right? So you did not have a lot of neighborhood peaks, whereas in this case the number of peaks in your neighborhood has increased, right? Slowly you are basically losing the value of your SNR, right? Whatever we discussed earlier. So if this is your noise floor, right? So this is your noise floor. This sort of increases when you go to on the right hand side version of the plot, right? Your noise floor has sort of increased. Okay, and so the ratio that you have with this weight that you have assigned to the peak component has sort of diminished, right? You had a very sharp ratio here, whereas in the right hand side the ratio has decreased, the SNR has decreased. And now if you have heavy noise, right, this has sort of, you still have this guy, right, but the noise has increased so much, right? Your SNR has become SNR is very poor, right? And you also have ambiguities, right? There are some peaks which are very high also, right? So there is a identifiability problem started showing up under heavy noise. Okay, and I show you an extreme case, right, where we have already lost track of the peak component, right? These have started coming up, right, and there is like everywhere there is some sort of noise that is present. Okay, so now we see that like now is it possible at all to recover this particular uh, peak, right, using this data, right? Let's say we are sticking ourselves to this data. We have seen that how the data could be deteriorated by putting more and more noise onto the samples. But see that we have used the FFT that has the same length. We are using the 64 component FFT, or basically we are calculating 64 frequency components, and of course we are only showing the positive ones, right, 0 to 32, only showing that 0 to n by 2 components, right? Now we are trying to see that whether using this data with very heavy noise, is there a possibility to recover? Okay, so if you I took the same sort of trace that has the same statistical behavior, it has the similar amount of noise that has been injected to the samples, and we try to see an exercise with very few number of frequency components and show you the gradation, right? We start with very few components, then move to higher number of components, which is basically this is a 32 point FFT, or a 32 bins, right? That effectively shows you like 16 positive bins, right? Next we move to 64, which sort of brings out, right, this area, because we are trying to we are kind of expecting a peak in this area, right? Because we know that what is the mapping of the frequency to the components, right? And next we look at the next two uh, FFTs in succession. The one is the 128 pins and the other one is 256. So if you see, if we are using a larger number of bins in your FFT while you are calculating the dominant frequencies, so you are inherently consuming more number of samples, and the value of your n is also higher. Okay, so what happens in these cases? The noise sort of subsides down. So basically, this acts itself as a noise filter, right? So your FFT is sort of acting as a noise filter here. Okay, so it's sort of improving the SNR, right, as you are increasing the number of components, right? So in this case, at least whatever we thought was sort of not recoverable, right, earlier, right, in this case we thought it is not recoverable at all, right? But if we just, instead of looking at 64 bin FFT, if we just increase the size of the FFT judiciously, right? I am not asking you to go to very high value, because again that is time consuming and that is like resource intensive, right? This computation, as we have seen, is pretty resource intensive, right? So if you are increasing the number of bins to 256, this kind of gives you a sort of a reliable peak, right? So I would say we can stop here, right? We don't have to go to like higher number of bins. Okay, so there is always a trade-off, right? How much large you want to make your FFT, and because that will consume more number of samples, right? And what is the noise that is present in your data? Okay, so under this very heavy noise, I showed you a demonstration where you can still improve the detection accuracy, right? If you are able to detect, so this is the signal that we are looking for, and we are able to detect it, right? We are detect the peak. So we are kind of able to successfully detect a peak, which is again a true positive, right? So of course you can detect peaks in the other cases also, right? But these are false positives, right? We are not interested about the false positives here. Okay, so now we are coming to the final concept, which is called a spectrogram, and we will see there is a lot of application of this representing the FFT data as a spectrogram to do miscellaneous things, right? When you work on real sensing problems, instead of looking at just one FFT, we look at a series of FFTs, and this series is directly mapped from how you see in this particular slide, right? Let's say you have this data which starts from 0, and continues, right? It continues, let's say, indefinitely streaming data, right? And what you are going to do is that, of course, you cannot use all the samples at one go. So you have a finite window, which I call the FFT window, and you are going to operate the FFT algorithm on this finite set of samples present in this window. So in case of this one, like 0 to t will span, let's say, 1024 samples or 256 samples, and you are going to compute the FFT that corresponds to only this 256 samples or the samples present in 0 to t, and then move the window. So we'll see what happens is, as we move the window, you can keep on computing these FFTs, right? So at every time t, small t, we'll compute extra FFTs in time, right? And it will be sort of spaced out in time, but there could be an overlap, right? We could make this overlap very high, or the overlap could be almost negligible. It is kind of a trade-off that we want to see, right? But what we are essentially doing is kind of a sliding window first Fourier transform. So from 0 to t, which is worth of the entire window, we calculate the first version of the FFT. Then we skip some values. We basically skip some of the samples, and then after skipping some, at a certain time, we start considering the values to be computing the next FFT. So this is your second FFT, or the second, and then so on, right? So, and there is a definite overlap that I have shown here, right? And this overlap would be same, right? It's kind of uniform across. Okay. So this FFT window acts as a queue, which has like incoming samples and outgoing samples, and you basically compute the FFT after every, let's say, small t seconds, okay, or small t time units. Okay. So from t to t plus t, and then t plus t to t plus 2t. So this is the worth of samples that you are computing your FFT on. Okay. So there could be an initial ingestion period, right? And after that, you can keep on churning out the FFTs. Okay. So what is a spectrogram? The spectrogram is a stacked up version of these FFTs. So what you have here in the x-axis is, given this is basically an n point or n bins or n components, right? So all you have here, if you are considering the positive frequencies, is 0 to n by 2. Okay. And in terms of time also, this is the time at which you are computing the FFT, right? So this is sort of a time frequency two-dimensional way of viewing the data. Okay. And how this is interesting and why this is interesting is, basically, often your events will be dynamic in nature, right? In case of the heart rate, of course, this is a dynamic in nature, but the frequency is not dynamic, right? You just have only one frequency, and that repeats over time. So if you, even if you take the time domain data for 5 minutes or 1 hour, right, there's nothing much that ideally should change, right? Unless and until there is some problem with the heart, right, where you will basically have the bits per minute will deviate a lot. Okay. Right, or you are not doing something artificially introducing some kind of a dynamism, right? If you are exercising and then you are not, and so on, in those cases you are going to look at different frequency values, right? So often, in case for such dynamic events, you might have the frequency peak located in different locations, right? So in the first 0th second, your frequency peak could be somewhere here, right? Whereas in the next second, it could be somewhere here, right? Not necessarily this is a second, but this is just the time worth of this number of samples, time worth of n samples. Okay. It could be here, it could be here, it could be here, right? And so on, right? So often the sub events, right? Because it could be also having multiple frequencies, because the event, we are not sure what exactly we are tracking, but there could be multiple spikes, right? And it's kind of important to keep track of those spikes, right? Maybe something like this happens. Okay, so we need to understand the evolution of these different sub events in the frequency domain. Okay, and this time versus frequency plot or the spectrogram can give you a very nice tool to do this. Okay, so what are the things that are normally done in this FFT window? This is a good place where we can filter out some noise, remove the DC offsets, right? Because this is not a very large period of time, and the kind of noise that we'll have in this small window, right? That could have the very same nature. Whereas if you pick up samples from a completely different place, right, the nature of the noise might change, right? So it's kind of a wise decision to look at the noise within a given window, get rid of them. If there are some arbitrary samples, like let's say there are like outliers and so on, so all the statistics that could be computed to figure out the outliers could be sort of local to the window, right? So this could be used for smoothing out the samples, remove DC offsets. We can adjust the overlap, right? How much of the overlapping? So when should we compute the next FFT window, right? Is it from here to here, or it's kind of more overlap, right? Whether it's kind of here to here, right? What should be the size of the FFT and so on. So these are some of the adaptive processing that we will do on this running data. So as you understand, this is like a running data, and we are discretely operating this FFT uh, operation every few samples, right? Which is depending on the amount of overlap we want to have, right? And stack them up nicely. This basically this particular figure, right, gives you the spectrogram. Okay, so now I'll show you a real example of a spectrogram where the frequency component, as you see, could change, right? The peak component, like let's say there is only one peak of interest, and this peak component that I have shown using this red color, right, changes with time, right? So these are the different frequency component, as you can see, which was actually picking up at the yellow color. The yellow color indicates a very high frequency component amplitude, and we are trying to track this peak component, right, with time. So this itself, such spectrograms could be a rich source of fingerprints, right, for different activities. Let's say if you are running, it is one sort of an activity, versus if you are doing some other, let's say you are doing some push-ups, right, in front of your sensor, right, that gives you another set of spectrograms, and there will be distinct difference in between them, as we'll see shortly. Okay, so if you can track something like this, let's say this is your frequency, right? So this in the y-axis you have the frequency, amplitude of a frequency, right? Or like what frequency is being picked, right? And then here we have time. And this could be a nice feature that could be trained to learn certain event. Okay, so maybe the change in frequency is very particular, right? From a very low frequency it goes to a high frequency, then it comes back with a certain gradient and so on, and all of this could actually mean a certain kind of a certain class of event, right? It could be a certain class of event, right? Or you can say activity, right? So the spectrograms are sort of very useful in mining such activity information, right? To classify activities, it would recognize activities and so on. Okay, so as you understand, this is a two-dimensional image, right? And this ML model could also mean you can train convolutional neural network like CNN, which is pretty useful tool for training the system from images, right? Now after you get the spectrogram, this is something that you can simply treat that as a 2D image, right? And you can have this collection of these 2D images corresponding to different activities or events, and for every class you can train a machine learning model, right, or a CNN model, right? CNN is pretty popular in training such 2D images. Okay. So this one example that actually I have performed, and using our IR sensor that I had already told you about from the very beginning, right? So you can very nicely see that while I was running, I started with sort of a very high speed, right? So you can say this is like a high speed, and then it sort of came down. It was kind of a low, I would say lower speed, right? And then again it went up, right? And so on. So those are like the micro classifications that you can do, but in a broad sense, right? You can look at very distinctly, right? Based on the behavior of the individual spectrograms. So one is the spectrogram that corresponds to skipping exercise. So I am doing skipping in front of that IR sensor, whereas in the other case I was doing a jogging, running, and so on. That gives rise to very different signature, right? Very different signature of the frequency components, right? If you compare some of these frequency components, whatever we see, all this high frequency stuff is not present right here, right? So there is a way to train the model, right? How the spectrogram should look like, and this is a typical way this CNN models would be trained, right? You can have a collection of the spectrograms that has been collected for skipping, and you can have a collection of the spectrograms that has been collected for running, and then you can train the system and test it out, right? And it's a very simple example of using spectrograms for activity classification, right? Just mind it is the IR data, but you can have other sensor modalities, right? If you are using millimeter wave or some other high-end sensor or a sensing modality, depending on what kind of resolution it can offer in terms of distance or in terms of sampling rate, you can do much more in terms of classification. Okay, so there is no end to it, right? I just gave you a simple example, right, to understand, right? There's a natural flow, right, after you have learned about how the coiling machine works and how the Fourier transform works, and this is basically stacking up the frequency components in the time domain, right? So you are basically having an FFT for every time. So this corresponds to one FFT, right? And again you have one more FFT. So this is somewhat stacking up the FFTs. So this is kind of a very useful feature, a very useful tool for doing such analysis in the sensing side. And this is the micro analysis that I was actually trying to show you in the very beginning. If you go and drill down inside a particular spectrogram, there are certain patterns that emerge, right? So one is like, as you can see, the speed sort of decreased with time, right? You can say that the speed decreased, right? And you can figure out how much it decreased, right? And then again it increased with time and so on, and then it actually jumped onto a very high speed, right? So this is probably very high speed, right? And this is sort of slow, right? So this is some kind of a moderate speed. And then apart from that, you can do other analysis. For example, you can also see that there are certain other things that are also coming, right? And often this is picking up reflections from other parts of the body. So typically, if it depends on which part of your hands and the legs was nearer to the system, right? So often this is your legs that are being tracked, and this is sort of your hand movements, right? So you can do those kind of analysis, right? And if you had a more sort of sophisticated sensor, you can actually figure out the movements of your head, the movements of your shoulder, the movement of your torso, and so on, right? So those are possible if you are using more sophisticated sensors. But for the sensor that I have used, this is a very cheap IR sensor, which is probably not very suitable to do this kind of analysis. Whatever I am doing is called your gait tracking, right? So what is gait is basically I'm tracking your head, shoulders, torso, different body postures that you are sort of making, and then trying to figure out the periodic nature of those particular things when you are running. Okay, so this is very rich in such features, right? There's a lot of information that could be embedded in a spectrogram, and you can mine those information for doing your sensing tasks. Okay? So the other thing that I just wanted to mention is, again, here the choice of n is up to you. If you spend a lot of samples in a given FFT, that is one thing, that you will basically get a highly granular sort of components. In this case, we are using a 256 bin FFT, so this is highly granular, like, right, granular. Whereas in this case, so where we are just using a 32 bin FFT, in this case we are using 64, and in this case we were using 128 bins. So this is, as you can very easily spot, that this is like very less granular, right? So if your just task is to figure out some sort of uh, variation of speed, right? If the problem is as simple as that, in that case, you can just stick to this kind of a figure, right? You can just stick to a 32 bin FFT, and very easily using some simple image analysis tools, right? You can try to figure out the edge, or you can try to figure out the maximum component and track that peak component. You can figure this out, right? And even you can have these indications for hands and legs separately, right? So that is also there. Okay, so if you want to look at more details, right, whether the movement that you are moving, you are making with your knees was exactly the same, whether you were, if you want to do some micro analysis of your gait, uh, depending on what kind of resolution your sensor gives, you can have a higher resolution data points, right? So this will kind of have a detailed information, uh, right? You'll have more number of frequency components in the area that you are interested in, right? Whereas in this case, you will see something that is more like blurred, right? You will see something like this one, which is not very detailed. Okay. So the spectrogram, we'll be using spectrogram in a lot of different uh, occasions later. This is a very useful tool when you look at frequency domain data and stack them up on top of each other. And from this image, you can do a lot of learning, right? Particularly if you are trying to classify or trying to recognize certain activities or certain events, this is a very useful tool that you should keep in mind. And with this, we are going to wrap up on the frequency domain analysis part. And from the next class, we are going to look at the other modalities of sensing. We'll start with touch sensing, right? And if you have any questions, you please let me know, particularly from the last two classes, the frequency domain analysis, right? And how we use the Fourier transform. And I would recommend all of you to actually go and implement the coiling machine on your own, and try to appreciate how this frequency components could be computed, right? So this is a must for all of you, right? This is again optional, but there's nothing to do with your grades, but this is really going to help you if you have an implementation done on your own. Okay, so I'll stop here. We'll see each other in the next class. Okay, thank you.